Okay, in the next two videos, I want to go over absolute continuity. And in the next video, I'll basically discuss kind of the deep characterization of absolute continuity and kind of the main point. Absolute continuity is basically equivalent to f prime existing almost everywhere, and the fundamental theorem of calculus holds. Very beautiful result. I think it's due to Lebesgue himself. The proof is in the book. Royden's book is probably as hard, if not harder, than anything we've done. So it's really, really deep stuff. I'll actually prove in the next video the easy part of that. So yeah, what's the definition? And it's sort of like, I guess, super continuity in some sense. So you can either state this for a finite closed interval or the real line. I'll make the necessary changes for the real line in a minute. So we say this is absolutely continuous on A to B if for any epsilon bigger than 0, there exists delta bigger than 0, where any disjoint collection of intervals AI to BI so here N, so this is going to differ a little bit from the book's definition, but basically by one of the book's homeworks, it is equivalent. So here N could be a natural number or could be infinity. Either one is fine. So we're going to look at countable collections of disjoint intervals or finite. Either one is fine. Clear if I put collection of intervals in A to B. That are small in the sense that this sum here is less than delta. We have the sum here of f of b, f of bi minus f of ai is less than epsilon. Okay. So it's basically there exists delta where this sum less than delta implies this sum is less than epsilon. And we do need to have a disjoint collection of open intervals in closed A to B. So each one of these is a subset of A to B. So whenever we have that, a disjoint, countable, finite, or countably infinite collection of open intervals in A to B, where the length is sum of the length is less than delta, the sum of f of the endpoints, f of b, a, bi minus f of ai is less than epsilon. So something kind of trivial. Absolute continuity implies continuity. Okay. So in particular, just set big N to be 1. And just look at a single interval. Well, if x is less than y, and both of these, let's say, are in A to B, So then, right, just basically set A1 to be X, B1 to be Y, and we have a disjoint collection, N equals 1, just one single interval. So then this yeah, I'll write it like this. And this is going to imply, well, f of x minus f of y is less than epsilon. Or maybe, right, to be maybe clearer. Let's say I have just arbitrary x and y in A to B. So this is less than delta. So if x is smaller than y, then yeah, n equals 1. A1 is x, B1 is y. If x is bigger than y, then just flip it around. Still n equals 1. A1 is y and B1 is x. So either way, right. So an absolutely continuous function on A to B has to be uniformly continuous, for example. Now, if this is on a real line, well, just replace this with the real line. And you really just, well, don't really need any of this. And we have the definition of absolute continuity on the real line. So it's basically whenever you have a disjoint collection of intervals with this sum less than delta, we have this sum is less than epsilon. Right. Usually you do this on a closed interval. And even sometimes there's some debate on like math stack exchange on the proper definition on the real line. It's a little obscure to do it on the real line, but the prelim does ask for it sometimes, and this is the definition. Focus on absolute continuity on a closed interval. All right, so what are some examples? Well, any Lipschitz, so we'll characterize absolute continuity in the next video. But one example is if f is Lipschitz, so if there exists m bigger than 0, we've done Lipschitz before in the course. You've done it in 511 probably. So f is defined on a closed interval A to B. So this is true for any x, y, and A to B. Then take something like this here. So let's say this is a disjoint collection of intervals in A to B. So I claim delta is epsilon over m works. So in particular, yeah, this less than epsilon over m implies, and all of these are in A to B, so it makes sense to plop it into F. So f of bi minus f of ai. Well, each one of these is less than or equal to m b minus ai. So this is really trivial. Lipschitz functions are basically trivially absolutely continuous. So in other words, any particularly you immediately get any function that has a bounded derivative on a to b by the mean value theorem is Lipschitz and hence absolutely continuous. Right, so this is less than or equal to the sum here, and you can pull out the m. Yeah, I'll pull the m out here. And that's less than epsilon because this sum here is less than epsilon over m. So yes, you don't need absolute values. I mean, you do. I mean, just from Lipschitz, you have absolute value, but because these are intervals, bi is bigger or equal to a. Okay, so something a lot more interesting is an example of something not uniform, not absolutely continuous. And that's a prelim problem. Prelim problem. So which is it? Yeah, it's August 2019. Is the function here absolutely continuous on 0 to 1? And the answer is no. In particular, this is interesting because this is differentiable on 0 to 1. You can check that it is differentiable at x equals 0, and you better be able to check that. Otherwise, you don't really understand Calc 1 differentiation, and you should go back and review it. And I guess it's not too important for the prelim, but just in general. But yeah, you can check this is differentiable on 0 to 1. But again, thanks to the mean value theorem. So the answer here is no. And this you can check directly that this is not going to have a bounded derivative on 0 to 1. The derivative will eventually blow up actually as x approaches 0. So in particular, make sure. Yeah, so this is kind of a neat little graph of the function here, x squared 1 over sine x squared. And you can see it's not really surprising that this would not be absolutely continuous. Because you just have really, really dramatic oscillation going on. Yeah, it just oscillates. I mean, the x squared here makes things go to 0 as x gets closer to 0. Because sine 1 over x squared is bounded between -1 and 1. So, I mean, I guess you might not be sure if the answer is yes or no, but the answer is no. Yeah, and for examples like this, if you kind of look and you're like, wait a minute, this thing oscillates wildly, then typically, the answer would be no. It's not. We proved something like this last time in the last video is not a bounded variation. This is very similar to that. Actually, everything I'm going to do in a second could be used to prove that this is not a bounded variation. But yeah, so let's prove this. Yeah, so I'll write down the example. Prove that f of x equals x squared sine x does not equal 0, 0 if x equals 0. It's not absolutely continuous on 0 to 1. All right. The only thing we need to be a little careful of is to always get disjoint collections of intervals in 0 to 1. And we'll check that. So yeah, there's a lot of different ways to do this. Probably the easiest way to do this is and I actually have to admit I forgot the easiest way to do this, so I did look it up. At least for the slight variation where we don't have squares here. But so let's say AN is, and this is not a very subtle choice of AN and BN if you think about it. And BN, set BN to be 1 over square root of 2 N parentheses. Right. All right, so certainly AN is smaller than BN because AN is the same thing, but we have this extra 1/2 here. So I have a larger denominator. But I claim, and there's really not a whole lot to prove, that AN is bigger than BN plus 1. I'll explain why that's important in a second. Yeah, there's really not much to this. 1 over, well, so yeah, so this is the same thing as saying 1 over AN is smaller than 1 over BN. So it's 1 over AN, it's just this here. Sorry, 1 over AN is smaller than 1 over BN plus 1. I think that's what I said before. But well, this is pretty, let me just try and squeeze this in. Right, so let's look at 1 over AN. It's square root 2N plus 1/2 pi. So this is certainly less than plug in N plus 1. Yeah, there's really not much. This is 2N plus 1/2 pi. This is 2N plus 2 pi. Yeah, so it's trivial, but this is really, really, really crucial. Again, this is 1 over AN, and this is 1 over BN plus 1. Okay, so what does this say? This says B1 is, let me do this down here. So N equals 1. B2 is less than A1, or rather, A1 is bigger than B2. Well, A2 is less than B2. Again, that's trivial just because the denominators are larger for AN than for BN. Okay. Well, N equals 2. This is bigger than B3, et cetera, et cetera. All right, so here's basically what's going on, not drawn to scale. Care, it's not the point. So we have B1, A1, B2, A2, I'll just draw the 2 more, sorry, B3. All right, so yeah, we're going to set each one of these to be my interval. So these are going to be my intervals. So they're definitely disjoint. I mean, we could even look at A1, B1, B2, A1, A2, B2, but there's no need for that. So yeah, so these are my intervals. So these are definitely disjoint. Okay. So the conclusion, and actually this is going to be pretty quick. These are disjoint intervals n 0 to 1. So in particular, for any natural number n, or rather, this limit here is going to be 0. That is crucial. Why? Because n equals 1 to infinity, bn minus an, that's a convergent sum. The sum is at, it's well smaller than 1. I mean, it's, what is the sum? Its sum is literally all these lengths. And I don't really have any desire to compute what the sum is, but, all these disjoint lengths are, they can't add up to more than 1 because it's so, right. So in particular, it's n equals 1 to infinity if bn minus an converges to something less than 1. So the tail converges to 0. So I claim that for any m, this is going to be infinite. And kind of thinking about what we did last videos, maybe not so surprising. So what is this? Well, oops. Did I use? Yeah, I used 2 different letters here. So I guess I'll go back to. Doesn't matter what letters I use. So let me go back to n. Just dummy letters. So. Okay, so yeah, there's really no subtlety here. Just plop it in and see what we get. So 1 over bn squared is just 2 pi n. Sorry. Sorry, so the function is x squared sine 1 over x squared. And none of these are 0, so we're always going to be using x squared sine 1 over x squared. So this is 1 over 2 pi n sine 2 pi n. Well, you better know what this is for any integer n. It's 0. And what is this? Remember what an is. It's pi over 2 here. 2n plus 1/2. So 1 over 2, 2n plus 1/2 pi. Sine 2n. So I'll write it like this, 2n pi plus pi over 2. Again, you better know what this is for each n. This is just 1. Sine's 2 pi periodic. So this is 0, this is 1. So yeah, what we're literally doing actually is so we're not going to deal with any of the negatives here, but we're going to compare yeah, so the bn gives me 0, so this would be like bn an. So this would be like bn an, bn an, bn an, bn an, etc., etc. So we're kind of just looking at this. I didn't even know I could do that. Etc., etc. Okay, that's what we're literally doing. All right. So yeah, so this equals, well, 1 over 2n plus 1/2 pi. Right? So yeah, we're done. And again, I want to just emphasize how dramatic of the failure of absolute continuity is. Okay. So particularly, so let me write it like this. It's not clear. So for each m, we have disjoint intervals in 0 to 1 that are the sum of the lengths is really small. I can make them as small as I want. But when I plug the endpoints into the function and look at the difference, and I sum up the difference, it's going to behave like the harmonic series, which for any m, the tail diverges because the whole sum converges to infinity. So this can be made as small as we want, but this, no matter what, goes to infinity. So yeah, so it's really, really, really dramatic failure of absolute continuity. Okay, so I want to do same prelim, summer, August 2019, a little deeper problem, which is number 6. So let's say G is an absolutely continuous monotone function on 0 to 1. E is a set of measures 0. Prove that G of E has measures 0. So you actually do not need monotone here. It just makes the problem a little easier, a little simpler. And if you want a challenge, try to do this problem without using the fact that G is monotone. Yeah, to make this problem a little quicker, particularly, we're going to assume, just like this prelim does, that G is monotone. And also, I think one of the prelim problems is, not in this one, but a different one, is if you have a set that, a function rather, that maps sets of measure 0 to sets of measure 0, then that function maps measurable sets to measurable sets. So this is the key property. This here is the key property that if E has a set of measure 0, then G of E has measure 0. This is the key property to proving that G maps measurable sets to measurable sets. So this is why this is important. This is saying an absolutely continuous function, absolutely continuous monotone function, maps measurable sets, measurable subsets of 0 to 1 to measurable subsets of 0 to 1. Right? And yeah, it is not true with just continuity. Okay, so how do we prove this? So let me get everything here for this problem. Okay, so the fact that we're on 0 to 1 makes this kind of a pain. So there's another prelim problem that basically it's a little simpler, and you should be able to do this yourself after you go through this proof. This is January 2023. Same thing, but assume F is defined on the real line. We talked about absolute continuity on the real line. So yeah, homework is do this problem. It's just a little easier than what I'm doing here. Very similar. Right. Okay. So, so proof of this problem. Okay, so the key simple thing but useful thing to note is that this is going to be, we'll take away these two elements and then add them. So not necessarily going to be disjoint. All right, so note that these are singletons. So in fact, this whole bracket here contains at most 2 elements. So it has measure 0, might even contain 1 element. So Yeah, as I mentioned, we don't really even know if this is measurable right now. I mean, it's true, but we need, as I mentioned, the key to proving that a function, one of the ways to prove that a function maps measurable sets to measurable sets is prove that it maps sets of measure zero to measure zero, sets of measure zero, which is what we're trying to prove. So that's why I'm going to use Lebesgue outer measure. So this is true if this has measure zero. So that's my task. Prove that this has measure zero. And why we're going to do this, I'll explain in a minute. So in a definition of absolute continuity, which I do not have with me right here, pick delta corresponding to epsilon. Okay. So use the definition of measure zero, pick a cover of E where this sum is less than delta. Okay. The annoying thing is we don't know that these are disjoint, and we don't know that they're a subset of 0 to 1, and in general, neither of them are true. Neither of those are true in general, unfortunately. There's no reason to think these are disjoint, and there's no reason to think that these are subsets of 0 to 1. One thing that is implicit in this problem is that this is a subset of 0 to 1. But otherwise, G of E doesn't even make sense. G is a function on 0 to 1. So this is less than delta. We can always do that. Okay. So we fix those two issues pretty easily. So yeah, how do we do that? So E is a subset of 0 to 1. This is why I want to look at E take away 0 and 1. This is convenient here. So E take away 0 and 1 is a subset of 0 to 1. That's going to imply that intersect 0, 1, it's going to cover E take away 0 to 1. So this covers E take away 0 and 1. Right. So I guess it really just follows. I mean, I don't even think you really need this right here. So it's really this would imply this pretty easily. But anyway, this and the fact that these intervals cover E. Okay, this is extremely useful. So let's assume that this is not empty. Right? Because if this is empty, then G of the empty set is empty. So then this is true. This is what we need to prove. This is what I'm trying to prove. Right? So if this is empty, so if E take away 0, 1 is empty, 0 and 1, that set containing two elements, that's empty, then G of it is empty, so it has measure 0, outer measure 0. So assume it is not empty. So what that says is E, so this is not empty. This is a subset of this union. So let's call this U, this union. So U is not empty. If U is empty, then E take away 0, 1 would be empty. So it's definitely a subset. It's the union of open sets. So it's a non-empty subset of the real line. So we can write U as the disjoint union of these intervals here. So we're writing U, we can always do that for a non-empty subset of the real line. We're writing U as the disjoint union of these open intervals. We're just calling it AI prime, BI prime, for lack of anything better to call it. So this is good, and I claim each one of these is a subset of 0 to 1. That's pretty obvious. Each one of these is a subset of U, and U is a subset of 0 to 1, open. So we have this collection of intervals that's a subset of 0 to 1. Also, let's look at this sum here, and I claim it's less than delta. So we can probably, hopefully, use this in the absolute continuity definition. We can, actually. So yeah, one thing I want to be clear with, if it's not, working with E take away 0 to 1 allows me to take the intersection with 0 to 1 of all of these, and that gives me an open set here. If I did intersection 0 to 1 closed, then that's not necessarily going to be an open set. I don't know what the hell that thing's going to look like. Yeah, so working with E take away 0 to 1 allows me to work with these sets versus closed 0 to 1 here. Right. And that allows me to get a non-empty open set, and I can use characterization of non-empty open sets as a disjoint union of open intervals. Yeah. Okay. So yeah, this is the measure of U because these are disjoint. Okay. Well, U is this union here. So this is going to be less than or equal to bicountable subadditivity. And that's less than delta because that's exactly how we picked these intervals here. This sum is less than delta. Okay. So this sum here actually is also less than delta. So this is great. This is perfect for absolute continuity. The sum here of these lengths is less than delta. They are disjoint. We get that from writing U as a disjoint union of these intervals. And they are each a subset of not even just closed 0 to 1, but open 0 to 1. So that's nice. So we're basically done. Right. So finally, let's assume F is increasing. I'll explain what to do if F is decreasing. It's kind of obvious, but. Right. So you do have to work even a little bit harder. It's not hard, it's just notation, and it just makes things longer. And like I could definitely I think I had something like this where I did not assume F was monotone on homework. I know I did, but you have plenty of time there. So, yeah, so we're almost done here. So, yeah, so G of E take away 0, 1. Let's just do this all in one shot. The outer measure of G E take away 0, 1. Yeah, to be crystal clear, this is takeaway. Well, that's going to be write it as equals. Sorry, it's a so E takeaway 0, 1 is a subset of U. So it is less than or equal to G of U. So this is going to be the outer measure of this union here, which need not be disjoint, but that's fine. So it's G of AI prime, BI prime. Well, this equals because G, well, sorry. We need to do one last little itty bitty thing here. So this is going to be a subset of G of the closed interval. That's kind of trivial. So it's less than or equal to the outer measure of the union of G of closed AI prime, BI prime. Now, by continuity and the fact that G is assumed to be increasing on 0 to 1, each one of these sets here equals closed G of A prime, G of BI prime. All right, so this is going to be less than or equal to, well, the sum of the outer measure of each of these intervals. I guess these two could be equal. That just means it's a closed, or sorry, that just means it's a singleton. That's fine as outer measure 0. So yeah, this I'll write it like this. I equals 1 to infinity. The outer measure of this interval, I'll erase in a minute because it's clearly the length. You really don't need, as G is increasing, you don't need absolute values. But it's less than epsilon because, again, these are intervals that sum up to less than delta. Each one is a subset of 0 to 1, and they're disjoint. So absolute continuity means we have all three of these true. That implies the sum of these is less than epsilon. Okay? So we're done. Finally, we're done. This, any epsilon bigger than 0 is less than this. So that means this is 0. Right? Yeah, so one more video on particularly the fundamental theorem of calculus and how it relates to absolute continuity. And that's really crucial for some prelim problems.